Here we have another example problem. The problem says a gas in a piston cylinder assembly is compressed from one pressure at a volume to a second pressure in a process for which the relationship between P and V is PV to the power of 1.2 is constant. The mass of the gas is given. During the process, the heat transfer from the gas is 2.2 kilojoules. Determine the change in the specific internal energy of the gas in kilojoules per kilogram. Kinetic and potential energy effects are negligible. So let's do this problem together. So we have this problem, and this is what our PV diagram might look like. We go from V1, which is the larger volume, down to V2. So we're compressing the system. So we're putting work into the system. So we would expect from our sign convention that work in is negative. We're putting work into the system. So we're expecting negative work in this problem. So now we know the governing equation delta U is equal to Q minus W. I can find my work. That's the integral of P dV. I'm trying to find delta U, so I won't have to do this, but in normal cases, we would find the change in specific internal energy, multiply that by the mass, and use it to get Q. But in this problem, we'll find the work. We know Q because it's given in the problem, and then we can use that to find delta U. So here we're required to find the total work. That's the first thing that we need to find. So we know that work is the integral of P dV. Now we're told that P times V to the power of 1.2 is constant. Or I can rearrange that to see that P is equal to some constant divided by V to the power of 1.2. So if I put that into my equation, because C is constant, I can bring that out of my integral, and I can see that work is equal to C times the integral from V1 to V2 multiplied by V to the power of 1.2 dV. If I do the integral, it looks like this. Now, because I have bounds on my integral, I can do some math and find out that C divided by negative 0.2 is equal or multiplied by this difference of these two fractions. Now, I don't really like my term outside the brackets being negative. This is just a personal preference. So I'm going to multiply both the term inside and outside the brackets by negative 1. So now my term outside the brackets becomes positive, and I alter the order of the two terms inside my bracket. So this is nice. I know V1 because it's given in the problem. I don't know V2 yet, and I don't know C yet. So what do? I'm always going to advocate that you should try to solve problems symbolically when you can. You can find a numerical value for C, but I'm going to show you a little bit of sleight of hand here to demonstrate that it's nice if we keep symbolic solutions here for as long as we can. So here you might remember that the problem tells us that P times V to the power of 1.2 is constant. And if that's true, then that means P1 times V1 to the power of 1.2 is equal to that constant C. But that constant C is also equal to P2 times V2 to the power of 1.2. Now, I can rearrange my equation above, and I can just multiply C back into my bracket here. But I know that C can be the left-hand side of this equation or the right-hand side of this equation. So now I put in two different symbolic versions of C because I want to be able to factor out V1 to the 0.2 and V2 to the 0.2. Now when I do that, I get that work as we go from 1 to 2 is equal to 1 over 0.2 multiplied by P1 V1 minus P2 V2. I still don't know V2, but now C doesn't appear in my equation at all. So now I've gone from two unknowns to one unknown, and I have a pretty clean looking equation. So now I got to find V2. And again, I can use this relationship that P1 times V1 to the power of 1.2 is a constant, so it must equal P2 times V2 to the power of 1.2. So I can rearrange this expression to find an expression for V2. Now, I can put in my values that I have in the problem. And the nice thing here is, because I've put this equation as a ratio of p's, and it looks like this should be P1 divided by P2, so there's a bit of an error in this case, but I fixed it down here when I did it numerically. Now, it doesn't matter what units I use for pressure here, as long as it's absolute pressures, because as long as they're the same, it works out. So I could change this to bars or atmospheres or pascals or kilopascals, but the ratio is going to be the same. So I'm going to leave it in bars for now. Those bars are going to cancel. And when I put that into my calculator, I see that V2 is equal to 0.136 cubic meters. So this is good because my volume is getting smaller, which is how I drew it out on my picture. So now V2 goes from unknown to known. So now I know everything that I need to know to find the work. So work is equal to this equation here when I put in the values that I know from my problem. So here I've changed from bars to kilopascals by multiplying by 100. But I see here that I'm going to want to multiply the kilopascals by meters cubed. So I'm going to change 1 kilopascal is equal to 1 kilonewton per meter squared. So I'll put that in here. And that means that as I'm carrying my units through, I see that both of these terms in my bracket are kilonewton meters. Now I remember that a newton meter is a joule, so a kilonewton meter must be a kilojoule. So when I do this, I see that the work, as I go from 1 to 2, is negative 76.6 kilojoules. So does that make sense? So we know that the units are correct because we're talking about work and we're getting an answer in joules. I know that the sign is what I expect because I'm compressing my system, so the surroundings are doing work on the system. So I expect this work to be negative. So the units are right and the sign is right. And that gives me some confidence that my expression for work looks pretty good here. So I don't know if the magnitude of the work is correct, but I do feel pretty good about my answer because the units and the sign make sense. But this is not what the problem asked me for. The problem asked me to find the change in the internal energy. So I need to go back to my first law. So if I make the assumptions that kinetic and potential energy changes are negligible compared to the change in the internal energy, then I get this equation. And now I know the work, and I'm told in the problem that the magnitude of the heat transfer is 2.2 kilojoules. But my first law equation doesn't ask me for the magnitude of Q. I need to know the sign. The problem tells me that heat transfer from the gas is 2.2 kilojoules. So when I read this, it sounds to me like the gas, which is my system, is losing heat. And I know from my sign convention that heat in is positive. So heat out, which I'm seeing in this case, must be negative. So my Q term is negative 2.2 kilojoules. There's two things that I like about this. First is that my units are units of energy, so that makes sense for Q, and it's the same units for work. So I have both of these energy terms in kilojoules, so I don't have to do any conversion. It's not like one is in joules and one is in kilojoules. So now I know both my terms on the right-hand side, and the problem has asked me what the change in internal energy, or the left-hand side of my first law equation, is. So now I start with my first law, and I sub in the information that I know. So I know that Q is negative 2.2 kilojoules, and I know that work is negative 76.6 kilojoules. Now, one of the things that's easy to mess up if you move too quickly through these problems is to forget that this is negative W. So negative W, so here we have negative of a negative number. So this is going to become a positive term here at the end. And again, if we move too quickly, we may have got the sign for Q wrong as well. So remember, we got to act like Dora as we're completing these problems, and we got to stop and think. This is a really good practice for engineers, no matter what we're doing. So when I put this stuff into my calculator, I see that the change in the internal energy is a positive value of 74.4 kilojoules. Now I got to ask myself, does this make sense? So U, capital U, is internal energy. So the units should be energy, right? And that's what we see here because we have kilojoules. But does it make sense that the sign is positive? So assuming that I got my magnitudes of Q and W correct, I see that the work is much more important than the heat transfer in this case. So the heat transfer is negative. So my system is losing energy because it's losing heat. But it's also gaining energy because we're compressing our system. So the energy that the system is gaining from the work is much larger than the energy term of the heat loss here, right? So it's kind of the work that dominates this problem. So it does make sense that U2, the energy in my system at the end of the problem, is bigger than U1 because the work we're doing on the system is bigger than the heat that we lose from the system. So that's the end of this lecture, and hopefully you're starting to get some kind of understanding of how we do first law type problems in closed systems. Next class, we'll learn a little bit more about how we start to find specific internal energy so that we can find delta U in problems like this without knowing the heat transfer. Thanks again for joining us on Thermodynamics. I'll see you next time.